So I wanted to make a screencast showing you just a review, a summary for constant velocity motion. Our general equations, our mathematical models to represent constant velocity motion. Okay, so these are going to be graphs and equations that represent constant velocity motion. Okay, so first we did the toy car lab, and we got a position time graph that was linear, something like this, right? And I just want to remind you that the slope, so the change in time this way, change in position this way, oops, that tells us the slope, which is a change in position in this case, divided by a change in time. I think in math classes you call that a rise over a run. Well, in physics we say it's a change in position divided by a change in time, because in this case we have position on the vertical axis and time on the horizontal axis. So change in position is our rise and change in time is our run. And we define this as our average velocity. So this is our later position and earlier position, right? So this is T2, this is T1, this is X2, sorry, my bad, that's X1, and later time is an X2, right? So we got X2 minus X1, those are positions, which is a vector quantity, T2 minus T1, and we called this average velocity. That was the name we gave this slope. And you could use the symbol V with a vector, put a little average there. Okay? And then we also had a corresponding velocity versus time graph. In this case, since our slope is positive, our velocity is positive, right? So if we find this area here, right, this area would be measured in, let's see, this axis is meters per second, possibly. That's one way you could measure velocity. Time's measured in seconds. You multiply those together, you get meters. And so this area here is a change in something that's measured in meters. Well, it turns out to be a change in position that would be measured in meters, right? The symbol is triangle with an X. So this is change in position. And the symbol we use is a triangle with an X. In other words, it's our final position or a later position minus our beginning position, right? And again, this was the area of our V velocity versus time graph, right? And the way you would calculate it in this case is you would just multiply, so displacement in this case is if you multiply this value, which is V average, right? And you multiply by T, and you get this area, because area is base times height, right? And then if we simplify this part, we get final position minus beginning position equals V av times T. And the beauty, largely, of physics, to me at least, is seeing how things connect together. So we get X final equals V average times T, right, plus our initial position. Okay, I love seeing things connect together. It makes me happy, okay? This equation here turns out to be the equation of this line in the form of y equals mx plus b. So I think that's kind of beautiful. Seeing how things connect together to me is very nice. So going down this way, the slope of our position time graph was our average velocity when we were dealing with constant velocity. And the area of our velocity time graph turned out to be our displacement, which is a change in position. And that's when you're going up this way. So we like to stack our graphs vertically so that we can make sense of things. And going down, again, the slope of a position graph, position time graph, is a velocity. And the area of a velocity graph is our change in position. Anyway, I hope that helps. That's a basic screencast showing you the general mathematical models and graphs that we use to represent constant velocity motion. Hope that helps. Have a good day. Thanks for watching.